Hello, good afternoon. Welcome everyone to this webinar, the latest in the CIBSE certification webinar series. I'm Andrew Gaines. I'll be introducing the speakers today and helping field your questions at the end of their presentation. Just a quick bit of housekeeping. You will get sent a copy of today's presentation and the slides and the recording subject to the presenters agreement will be on our new section of our website, hopefully from tomorrow. So let's get to the presentation. I'll leave the detailed introduction to the speakers because they'll do a better job than me, but we have a team delivery this afternoon, hoping the technology works for that. Phil O'Loughlin, Michael Pollock and Colin Rees of IES, who will be talking about the use of the IES software with TM54. So I'll probably hand straight over to Phil, who I think is the first speaker. Over to you, Phil.
Oh, hi, good afternoon. I'm Phil O'Loughlin. I'm the consultancy team project manager at IES. I'm a chartered engineer and one of the originally certified level 5 CIBSE energy assessors. So I've been around for a while. Joining me today is Colin Rees, who is the consultancy manager, and Michael Pollock, who heads our special projects department. And together we're going to take you through a progressive approach to TM54 design stage operational energy assessments. Okay, so we'll take a look at what opportunities we have to improve the accuracy of our energy predictions based on the TM54 methodology. Colin will take us through the importance of a connected approach to energy modelling from the outset. Michael will go on to discuss when to consider and the advantages of detailed HVAC modelling. Colin will then come back and have a discussion with us about post-occupancy evaluation and the important improvement for a newly developed project. On completion, we will have time for some Q&A and some discussion. It's probably worth noting, before I go any further, to just detail what we don't intend to cover. Primarily, this is because it's generally subject matter already covered in this series of webinars. For information on repurposing an energy compliance model, take a look at the excellent earlier webinar by Nishish Jain from UCL. This provides a great description on this procedure. The performance gap disparity that is found between the energy use predicted and carbon emissions in the design stage of buildings and their energy use of those buildings in operation is also well discussed in previous sessions. We also won't be discussing legislation around building energy consumption simply because we haven't got the time. So I'm going to start off with a bit of history, and I'm going to show my age here because as a child I can remember the 1973 energy crisis. I recollect my father, a building services engineer himself, visiting schools to replace bimetallic thermostats with tamper-proof versions. These thermostats were set to 61 degrees Fahrenheit or around 16 degrees C in modern parlance. I also remember the exciting scheduled blackouts that we had to have and getting the candles out. Shortly after the crisis, the government began encouraging energy efficiency with advice and incentives. CIBSE published the Good Practice Guide on Energy Efficiency in Buildings in 1997, which included a comprehensive set of energy benchmarks for buildings titled Energy Consumption Guide 19. Subsequently, TM52 was published in 1999. This was really aimed at energy consumption in existing offices, offering a procedure using spreadsheets to provide an assessment and reporting methodology based on unit floor area for benchmarking against data in the energy consumption guide. This was further updated in 2006. In 2008, CIBSE published TM46 and 47. These documents provided building energy benchmarks to complement the operational rating procedure developed by the CLG for their display energy certificates for use in England, Wales and Northern Ireland. This document was revised slightly in 2010. So as we progressed into the last decade, the AM11 and other reference documents became increasingly important to building services engineers as the interest was honed on how much energy our buildings was going to consume. TM54 was launched in 2013 to provide the building designers and owners with clear guidance on how to evaluate operational energy use more fully and accurately at the design stage. The Right Honourable Lord Kelvin is famously quoted as professing, "To measure is to know. If you cannot measure it, you cannot improve it." This is a great mantra that we follow at IES and clearly illustrates the need to better understand the operational energy of our built environment right from the design stage. If we're to move forward in our quest to reduce energy consumption, this is an absolute must. So moving on now to look at the current guidance and the approach provided in TM54. The methodology set out proposes that the energy use of complex systems such as the heating, cooling, humidification, dehumidification, ventilation systems should all be evaluated using some form of dynamic simulation model. In our case, it would be the VE. I've highlighted this in the yellow table here. But steps 3 through 9 lie outside of the model and are based on historical data, factors, and heuristics. To progress, we will try to improve on some of these elements. So why should we try and take this progressive approach? Well, this is a mouthful for me, but we want to try and reduce the width of the variance whisker from the median to improve the certainty of the actual realization of the modeled predictions. So, as I say, it sounds like a mouthful, but put simply, we're trying to reduce the error bars on the top and bottom of the predicted energy use. We'd also like to try and reduce the amount of time spent on ad hoc manual calculations. One complaint I often hear about real operational energy calculations is the amount of time it takes to produce them. And we'd also like to make it quicker and easier to make comparative assessments based on changeable variables such as occupancy or particularly in these challenging times, differing occupancy density, for example. And then the next question I guess we need to ask ourselves is, when should we take this progressive approach? Well, only when energy being assessed is initially shown to be significant. For example, modern buildings consume considerably less energy to heat them these days than they used to. If the contribution to the total energy load is minor, then there may be little point in honing its accuracy under certain circumstances, depending on the nature of the study, of course. And we also need to consider why the forecasted operational energy is required in the first place. Is it simply for interest? Maybe BREEAM is asking the question, or possibly a rental or PFI agreement. Maybe it's to form part of a funding bid for a replacement leisure centre or something like that. All of these questions need to be posed before we embark on the study. Sometimes the end client is intent on embarking on a continued monitoring and improvement process post-occupancy, such as creating a digital twin or a continued interest in their energy use. More on digital twinning later from my colleagues, but certainly it's looking like the future of how buildings are designed, maintained and taken forward. Okay, so in an effort to improve the approach, we would like to find ways to bring steps 3 through 9 into the DSM model. We'd also think it's sensible to improve the accuracy of the assessment of artificial lighting, and then, where viable, improve the system modelling of HVAC systems. When carrying out TM54 studies for our clients, we have found that the information flow from the model and the previously mentioned calculations that sit outside of the DSM can make communicating the findings disjointed and provoke issues in reporting. Even worse, without care, consumers of energy can either be overlooked or double counted. To combat this, with careful planning, we can interpret the findings of some of the steps and loads that remain static throughout the year into templates and profiles within the model. By taking this approach, we can bring all the energy consumers under the umbrella of the model to simplify evaluation and reporting. Once we have decanted our loads, before doing anything else, we need to map out the metering, primarily with information provided by the M&E designers, and then, if necessary, split further to enable analysis and identifying the heavy or even light consumers of energy within our building. A well-laid plan will help as the model progresses. Colin will discuss model forward planning in more detail during his section. Okay, taking a look at some examples. If we have a look at catering, TM50 provides tabular historic data on the environmental and operational likely consumptions per meal. We can deal with the environmental loads within the model in the usual way, leaving us now to sort out the operational loads. By first assessing the total annual energy load based on the client information or data within TM50, we can take this back and granularize the information into a template. We can then profile it to a daily, weekly, and annual use, assign a meter, and therefore be better placed to assist not only with the estimated annual energy use, but also peak maximum demand. Just another example, looking back at step 4, which is vertical lifting. This is always difficult at the design stage, as generally speaking, a lift consultant is often yet to be appointed. Picture the scene. The architect will know the size of the lift shaft. The electrical engineer will probably know the size of the load of the motors that need to be driven, and the mechanical engineer will have an idea of the ventilation requirements. But none of this helps to deduce the annual energy consumption. By review of ISO 25745, we can agree with the design team on a suitable energy efficiency class for the lifting equipment. Once this is established, we can work back from there to gain an estimate of a suitable loading profile. Again, if a relevant consumer, this can be honed at the design as the design progresses and a lift consultant becomes available. TM54 directs us to use the Lenny approach to calculate the lighting energy use over a year, as laid out in the formula shown here. The Lenny calculation uses factors to account for occupancy, daylight dimming, and adds parasitic loads to account for the emergency lighting and the control systems. Using ray tracing tools within DSM software, in our case it would be Radiance, we can link the actual daylighting, and with careful zoning the annual energy consumption can again be granularized and better understood over the course of the year of the loading. In one example, as seen here, we found that by dynamically controlling the overall lighting load, the annual consumption was 58% of that predicted using the Lenny approach. Also see the load through the year here, again important for peak maximum demand. A similar approach to internal lighting is suggested in the TM for all other lighting, such as external car park lighting, task lighting, and display lighting. In another example, using a profile based on global radiation to represent the operation of a photocell linked lighting control system, we found the Lenny to be circa 60% underestimating, as indicated here by the blue bars, the grey line being the Lenny approach. However, we then found that should the designers decide to include a time switch to terminate the lighting, in this case it was at midnight, and then make the lighting again available at around 5 AM, the energy consumption reduced to 58% of that by the TM54 method. Again, this is using the operational study to assist in developing the design thoughts in collaboration with the designers. I'm now going to pass over to Colin to discuss an approach to planning your modelling and improving consistency through the process.
Thank you, Phil. Good afternoon, everyone. Colin Rees, Consultancy Manager at IES. I'm just going to talk a wee bit today about how we can actually plan out our energy modelling and some of the issues that are related there, and how we can maybe take a better approach to building that together towards what would be a functional TM54 model, or as a more progressive approach as an energy model, which kind of takes the next step on from that. Now, we know that there's a lot of stakeholders involved in project teams. So we have our clients, our architects, designers, contractors, and every one of these has a different viewpoint on how the project should progress. They've got their own issues that they want to look for, and obviously try to appease through the project. Now, it's imperative, obviously, that these need to align with the actual project objectives in order to achieve a successful building outcome. But in a lot of cases, there's obviously some conflict that can arise, and then the result of this is that you have a risk to those. Now, in terms of the TM54, that's obviously an energy performance, but there's subsequently an impact to your carbon, cost, and any other related sustainability objectives. And that is essentially then an impact and a risk to your performance gap issues in terms of projects. I'm sure everybody's familiar with that term, and this is particularly a connected approach is how we could look to close and eliminate that performance gap within our designs. Now, obviously, design is fluid. There's a number of stages to progress through to before we achieve a building and operational process, in which case there's a number of stages that are obviously going to we have to pass through to ensure that we've got a kind of a successful building, and that then gives rise to situations where we can have risk developing from that. So one of the things that we should really be looking to do in a connected approach is setting a kind of a plan of action in terms of how a project can develop from the outset. Now, this can involve setting and defining the team roles and responsibilities that's going to help support high quality energy modelling within the project team. Now, commonly, the modeller may be seen as a lower role, but obviously we're in the belief that this should be elevated, and that the modeller can become a central focus to help guide and drive the project within this process. Now, to ensure that's going to be possible, obviously we want to look for competent modelers, and that should be something that design teams should be, project teams should be looking to ensure that they have that available there, so that they can rely on the modelling being performed throughout the stages. Now, TM54 obviously serves as a basis for a modelling process, but what we want to do is take that and then map ahead for the project team how the stages are actually going to link together. So if you're moving through your concept, spatial coordination, detailed design, how does the TM54 assessment actually fit within those that you can then prove that it's going to be successful? So creating a roadmap or a route ahead of how you're actually going to link in your types of modelling is going to serve a very successful process to ensure that you're actually, first of all, analysing all the aspects of your design that you're interested in, and then able to kind of group together the feedback from that modelling into making sensible and accurate decisions that are going to benefit the project. So this modelling roadmap, this could be developed as it goes through to suit the design. It can be flexible, and it should be to suit for that. But having that roadmap ahead at the start certainly gives a strong point to learn from projects. Now, previous projects are obviously there as a good starting point to learn from. What were they successful? What were the issues that should have been learned from? And what data could be taken from those projects as well. Now, one of the things commonly that's discussed on energy modelling is, well, how do we gather the data together to ensure that that's available to kind of populate and seed a TM54 model? Well, that's where it needs to be a process put in place to decide, well, whose responsibility is it to gather something like the lighting data, the equipment data, what can be taken from previous projects or similar building types that you may have performed analysis on, and start to identify, well, where are the data gaps that the team need to start to source that from to kind of filter through. It's not always the case that the data is available right from the start. So that's something that can be fitted into the map is, right, what data do we have available now, and what length of time and source are we going to actually bring the additional data that we need to start to layer up our energy model as we go through into the later design stages. And it's a case then of repeating that process as you go through and building up those layers to reach to a point where you've got a more detailed energy model. So how would this look perhaps on an example stage? Well, I'll come to that. But really what we want to do is kind of make sure we've got a focus on what our deliverables are going to be in the project. Now, with anything like an energy model, there may be some other aspects you need to be focused on. It could be overheating, it could be daylight. So how do those link in, and how can you ensure that you can consistently track the deliverables that are going to measure your building performance, as Phil mentioned earlier on? It would also be a successful route would be to agree a set of results formats to ensure that the project team can read over that. Essentially, think about it in terms of the same language on the reporting structure. Not always the case that designers and clients are understanding what's produced. So if you're able to agree that structure beforehand, everybody has an awareness of what to expect once the modelling is completed and the results are available to review over together. And you want to continue to track those stage outputs for continued reference. Just because we move from a concept stage into a spatial coordination doesn't mean that we're going to be seeing superior results. We would plan to, but you'd want to be able to review back to the previous stage results to ensure that you're actually seeing a performance benefit. And that may be on your energy, it may be on temperatures. As I say, there's various options that we can actually look at when it comes to modelling. So if we were to look at, say, for example, a REBA stage 2, which is our concept, then a kind of a roadmap that you may want to look at would be to, first of all, set out the analysis that we want to evolve through the design, and then start to bring together, well, what is the data that we require there? So climate data is obviously going to be a key aspect. What's your location? What data do you have available in weather files at this particular point? Obviously, CIBSE have got a series of files available for locations, and that can include present day data as well as future weather files. But there are a number of other options available to be able to source data together. That's a kind of a library which is very much a growing resource for modelers. There's lots of files available to be able to source. And it's a case of looking at what files are maybe available and reviewing those in advance. Identifying the model inputs. Is it, as Phil's talked about, there's various stages and types of data that go into a TM54 model. So identifying what you're wanting to source at that particular time and then seed into your model. If we're going to be doing modelling at the concept stage, then we're going to be having also a focus on concept forms. So if that was a case of looking at some solar exposure, looking at the number of hours and the rate of solar radiation that may be on certain facades, which areas are the most shaded, which are the most exposed, which would help to drive any window to wall ratios, solar shading layouts that you may be contemplating. But your roadmap would be driving that assessment and setting out what you're going to assess and how you're going to report that. Then there's also the case of doing thermal modelling, but starting first of all with a lighter touch, or by doing sensitivity modelling. Identifying spaces that may be the most common within your buildings, looking for winds on their energy performance first of all, and then repeating that throughout the rest of the building. So if you had, for example, a school, then obviously you could focus on the classroom. With a healthcare building, obviously something like a small consultancy space or a ward that you could focus on, do very quick analysis and integrate and analyze aspects such as your glass types, your constructions, your internal gains and the performance of those. And then building that into your full energy model, which you would then be developing for your whole building. And as Michael will talk about shortly, that can then include populating it with HVAC. And all that then together with recording your stage findings, which would then drive your performance to the next stage. I'll just finish with a few points here on the benefits. And that's obviously a focus on the building needs. You've outlined at the early stage the kind of the key design considerations that you're going to focus and look for answers on. And it also ensures that your team are united on the objectives for that common goal of your building performance. Now, if you're working towards a low energy and potentially a net zero carbon goal, then there's obviously got to be quite a lot of analysis that would be performed to ensure that's going to be the case. We talked about high quality data being sourced to the modeler so that they can include that, and then you've got reliable data on for your assessment. Taking modelling methodologies, something like the sensitivity modelling, producing peer reviews to ensure that's up to a high standard, and then obviously setting a clear expectation on modelling time and managing those expectations in terms of delivery. With the map ahead you can set, well, this is what we're going to define as our time period for our modelling, and what our expectation is in terms of the delivery for that. And then that's that greater potential being achieved then for further analysis, and that the reward of a lower energy performance. And that really is the kind of the case of taking that on to that kind of next step of building your modelling there, and providing the kind of the overall performance proof. I mean, energy modelling has been proven to provide a cost benefit. Modelling at the earlier stages definitely provides a benefit in terms of the operational side, and I'll show that a bit later on. But certainly at IES, we've been focused on doing that for a number of years now, and we've got a number of examples of kind of taking that through into the kind of the track as I've shown there. So what I'll do now is I'll pass on to my colleague Michael, and he'll take you through a wee bit more on the HVAC analysis.
Thank you very much. Good afternoon, everybody. My name is Michael Pollock. I'm a project consultant with IES, where I lead the special projects team. I specialise in detailed HVAC modelling, and I'm typically involved in working on ASHRAE 90.1 sort of projects for lead, and also energy models for operational models that incorporate detailed HVAC simulation. Over the next 10 minutes or so, I'm going to talk about the detailed HVAC modelling and its importance within operational energy assessments. Now, an important factor in accurately modelling the operation of building is to ensure that the HVAC systems that are designed are accurately being reflected within the analysis. With a detailed HVAC model, designers can understand the intricacies of their system's performance, giving them the information to help design the most appropriate system for a given situation, or a given design. With simpler system modelling options, like the ones used in the National Calculation methodology, they can oversimplify the complexities of the system operation and leading to less accurate predictions of energy use. To give an example, in the case of the NCM methodology, a building's fan and pump energy is simplified down to a static auxiliary energy value, which is derived from one of 4 equations, depending on which system type happens to have been selected. Now, this can result in very different systems with different characteristics, ultimately predicting the same energy use, where in reality they would be very different. An example of this would be if you were to do a comparison between a variable air volume system and a constant air volume system. While you would expect the variable air volume system to document a lower fan power, because both systems use NCM equation 9 for auxiliary energy, both predictions would come out to be the same. And this is where detailed modelling, detailed HVAC studies come into their own, in that we can model the systems in far more detail. Now, within TM54 itself, jumped ahead of it. Within TM54 itself, it identifies that the section 711 is outlined the calculation process for determining energy use for space heating, cooling, fans, and pumps. Now, while it doesn't mandate the use of detailed sort of analysis, it does recognise that using a detailed HVAC analysis tool will give a much better representation of what happens in reality. The following section in TM54, section 712, describes the energy use associating with humidity control within the building. It again identifies that where a building needs relative humidity, perhaps in a swimming pool or a gallery or museum or something of that nature, where humidity needs to be closely controlled, then it recommends the use of a detailed DSM model. This is largely due to the very large energy requirements involved in cooling air down to below the dew point, and then subsequently having to reheat that air. This can be very energy intensive, and in simplified approaches, you can be underrepresented. Okay, in a detailed HVAC model, every component of the building system is individually modelled. That includes every fan, every pump, and every coil. So we're no longer just looking at a single overall system value. Each individual component will be populated with its own characteristics that describe its capacity and performance under different scenarios. The detailed HVAC model is also controlled in a manner that reflects how this building would be operated in reality. For example, airflow controllers will be configured, potentially that will modulate the amount of ventilation that goes in based on a CO2 concentration within the space. Similarly, fan coil units would be continually moderating their output for heating or cooling depending on sensed temperatures within the room, again adjusting potentially airflow rates that are passing through the fan coil unit itself. At every single time step, the performance of these components, whether it's the energy consumption, the loading, the capacity, is being continually assessed. So we no longer just have that as a single value, but we're getting a much richer picture as to what's happening within the system. Now, not only are each of these components being simulated, but it also allows users to interrogate every one of these components to get a very detailed breakdown of how the system's performing, where the energy is being consumed, and so they can target strategies to how to further reduce the energy consumption, where they see potentially air handling units that are consuming a larger proportion than other similar ones. Okay. Now, again, unlike a simple HVAC assessment where fans or perhaps just have a single specific fan power being used to represent their performance, with a detailed HVAC simulation, we set up performance curves, in this case a fan curve, to represent how the fan power will change under different flow rates. So again, throughout the simulation, in a VAV scenario where the airflow rate is continually changing, it allows us to capture the energy consumption and the potential savings that we could be achieving with a VAV system, which is something which, as I mentioned earlier, doesn't necessarily get captured following the NCM approach. Okay. As the fans are explicitly modeled, designers can experiment with different configurations of their HVAC systems to understand how relatively small changes in the design can affect the performance. One example of this might be with a fan coil unit installation. This could potentially be configured to have air coming in, fresh air coming onto the back of the unit, or with a separate ventilation supply going into the room. Now, depending on what configuration is used, if the ventilation was going onto the back of the fan coil unit, then that fan coil unit is going to have to run throughout all the occupied hours to ensure that ventilation gets applied. This can have a significant impact on the resulting fan energy, which this type of analysis using a detailed HVAC model will provide the designer information on the implications of these design changes. Now, similarly for heating and cooling plant, under kind of simple systems model, the plant efficiencies would typically be represented using a simple seasonal coefficient of performance or seasonal energy efficiency ratio. Now, these SCOPs and SERs are generally determined from standardized load weightings and standardized outdoor air temperatures that don't necessarily reflect the real design conditions. Now, under a detailed HVAC analysis, the heating and cooling systems are going to be modeled using a series of performance curves to accurately predict the plant capacities and efficiencies under constantly varying part load and temperature conditions. The screenshot on the slide at the moment shows one of the performance curves for, I believe it's a VSD chiller. So at every time step of the analysis, depending on the loadings, the chilled water temperatures, again the outdoor air temperatures at a given moment in time, the efficiencies will be continuously changing. Now, as the performance of the system is calculated each time step, the resulting energy consumption will be far more accurate than simply using a published seasonal average. Okay. Now, Various control strategies can also be modelled to help optimise the performance of the building systems. Now, this might include ventilation control strategies such as CO2 controls, alternative boiler and chiller control sequencing, or looking at temperature resets on the hot water loop and the chilled water loop in order to optimise boilers and chillers efficiencies. By using a detailed HVAC model as part of an operational model, the design can be tested to see how effective it is at maintaining the design conditions and can be used to flag up any potential issues early enough that they can be rectified. When using a simple approach to modeling systems, it can be easy to overlook important factors. If a simple approach were to be used to compare, say, a fan coil system against a chilled beam solution, then the chilled beam would likely come out on top, simply because the chilled beam doesn't have the terminal fan, thus it will consume less energy than the fan coil unit that does have a fan. However, by doing a comparison using a detailed HVAC, then intricacies such as ensuring the room dew point temperatures don't drop sufficiently low that condensation becomes an issue with the chill beams, and what impacts we see from running at higher water temperatures in the case with the passive chill beams can also be interrogated to give us a much more accurate comparison of the potential advantages and disadvantages of the two different systems. One other example where we can utilize an operational model to potentially identify sort of issues would be with an air source heat pump solution. Now, air source heat pumps are becoming increasingly popular as the electrical grid continues to decarbonize, making heat pumps generally a good solution for a low carbon design. Now, the rated capacity for a heat pump that we typically see published will be documented based on an outdoor air temperature of 7 degrees Celsius and running at a hot water loop temperature of about 35 degrees. The chart I've got on there illustrates the performance curves from a heat pump that I've been working with recently, where we can see that the capacity of that heat pump varies significantly depending both on outdoor air temperature and the operating temperatures. Now, what we'd want to ensure is that the heat pump that gets selected for the job can not only meets the capacity at its rated conditions, but also can also meet the design conditions based on the temperature design temperature for the system and the design ambient conditions for whichever site. Now, if this were to be a problem, then this is something which would be evidenced in the operational model, where if we had an undersized heat pump, we would start to see issues with space temperatures not being met. So there'd be a number of unmet load hours where rooms were not meeting their heating set point. That would be a red flag that there was a potential issue with the design that we would want to look to rectify. Now, the TM54 recognises that creating a detailed HVAC model can take more time than taking a simplified approach. There is, however, a catalogue of prototype systems incorporated within the software that can be imported into any project, and auto-sizing tools that ensure that the imported HVAC plant can be suitably sized. This gives designers the ability to experiment with different HVAC solutions much earlier on in the design process. As mentioned previously, different systems will each have their own advantages that will make them more or less suitable for given applications. Buildings which will have high internal loads may find that they're better suited to a centralized VAV system, where they can make use of free cooling using outdoor air. Whereas buildings with small internal gains may find it more useful to have local heating and cooling, where it's more effective due to lower fan powers that are involved. There are also likely to be other practical considerations as to the availability for ductwork for a given application. Now, making use of detailed HVAC models early on in the design can help inform designers on the strengths and weaknesses of the different approaches and help them to identify the most appropriate solutions early on in the design. Now, I'll pass over to Colin next.
Thank you, Michael. I'm just going to finish off our presentation just talking a wee bit about operational energy. At IS, we've been investigating a number of operational energy models by using an energy model taken from the design stage and then integrating that with further data to assess how it actually performs in real life. Now, when we move from the design stage, our kind of goal to reach and assess the operational energy is to have a fully aligned energy model with an HVAC network, as Michael described, and also a metering strategy, as Phil would quickly noted earlier on, that is in line with what's obviously the BMS and metering strategy was in place through the design, so that both are synced together, and that way we can take data from the operational model and bring that into, from the operational building into our operational model. Now, this then can stand as what I would call as a beacon to ensure that your performance objectives have been reached, so we can use that operational model to test and then ensure that the performance of the building, not only from doors open, but obviously the life of the building. In some cases, we can be talking about a building that's 40, 50 years in terms of its lifespan. You can then take that and then start to assess in terms of post-occupancy, but also forecast any potential building change, which may be a retrofit design, or take account of any future climate impacts in terms of a changing climates, so that you can fully assess any measures to ensure that your building is still high performing. If we take a quick look at the next slide here, we have measured data which we brought into our iScan platform on the top left, and that is the building submeters. We've then been able to calibrate our model in the VE model in the lower right, and ensure that we can then match the performance of our model to the real life scenario. And then once we've got that model set up, it gives us a great opportunity to really look at how we can ensure that the design has met its particular objectives, and if there's changes to the building that need to be taken account of to ensure it matches the design. So to do that, we can also take real climate data from the time period that the measured data has been extracted. As I said, there's lots of opportunities to take weather files, and that also includes real climate data can be sourced for the periods, weather files created that you can then use as your external test conditions. And you can then begin the process of creating your calibrated energy model. With that, we now then have an opportunity to mirror our operational building and perform that post-occupancy evaluation and seasonal commissioning. So what fine-tuning needs to be performed in the building still? We can dig into through the operational model where those issues are actually existing. Is it in some of the controller options? Are we not meeting our fabric performance? Is it on infiltration? Or are there some issues to perhaps do with our lighting and equipment usage is over and above what we predicted in terms of our profiles? But we can create a certainty and a reliability for the building's operation by using that calibrated energy model, and we can provide that on both the energy savings, zero carbon status, and obviously what the building's running costs are going to be through its lifetime. And that essentially then creates what we call a digital twin that you can then take and put in place for the building team in terms of also any future planning considerations. So that ties up our presentation. Thank you, everyone, and I'll pass over if we may have some questions that we can take.
Yeah, thank you. I've kept an eye on the questions coming in. We've got a few, some quite specific, some a bit more open-ended. We have one question come in before the start about where you can source inputs for information for lifts and server rooms. I think lifts were covered in the presentation, but maybe not server rooms. So that's something you can say something about quickly, Phil?
Yeah, I mean, the information sources are becoming more and more prevalent now, as the need to know what your buildings are consuming. So I'd probably, the first place I'd start to look is things like the CIBSE energy benchmark tool, which is available online, or the Better Building Partnerships is another good resource, or even Landmark has the display energy data there that's available. A little bit older is Guide F. I think Guide F might be 2012 now, but certainly a useful resource for information. And the best place for information, or the most accurate, I would suggest, is if your client has a portfolio of buildings and they've gathered data, then their energy use as a business is almost always going to be the most accurate source of information.
Okay, thanks. We've had a couple of questions about calibration. Would it be possible to expand on the calibration process? Is there technical advice available or rules of thumb? And with the information provided today, can you cover what you did to calibrate the model?
Yeah, I mean, that's a developing process. I mean, with calibration, there's a lot of data involved, and that's something that IS that is a service that we offer. It's a skilled process. I mean, I showed the graphs there in terms of bringing in the meter data from and then putting it into our iScan platform. So there's certainly there's a process of being able to see the data within there, visualize and understand if there's any data gaps in that. But then you can also then bring that data and sync it into the VE model automatically. So there is a process there where you can link the two, the iScan platform and the VE model together. That's something actually that Michael's performed on a recent project, and hence where we kind of added those charts into as the example in today's presentation. I think probably in terms of the process itself, it's probably too detailed for today's session, but I'd be more than happy to discuss that at a later date.
Okay, thanks. I think this is a good one. Is it possible to interface with a physical BMS system to get direct feedback into the model?
You can. Again, that's the kind of the purpose of iScan, is that you can automatically set it up to bring in data from your building meters, and then from there have it housed within scans so that you can interrogate it, and then once it's stored within there at the appropriate time, bring data sets synced into your model. So you may want to be doing that at quarterly time periods, perhaps, to assess how the seasonal impact is coming through. But as a process, it's certainly something that we have performed.
Okay, thanks. Next question is, would you use HVAC modelling for modelling processes in an industrial setting, for example, a beverage factory that might be using the air source heat pump for heating and cooling of water for processing of the drinks, so not related to building operation?
I would think that would certainly be a good application of it. Certainly within the virtual environment, one of the options that we have when setting up our loads, it isn't just for loads associated with coils, but we can also set up scheduled heating or cooling loads onto the plant. I've used it in previous times to model, loads for heating up swimming pools, for example. So it's in addition to space heating. But absolutely, we could, if you had a schedule for that heating demand, you could certainly apply that within your model, so that you're capturing the energy consumption associated with your heat pump. If that is a reversible heat pump, that could again be tying into some cooling process happening elsewhere on the system. And that's not something you'd be able to do with a simplified model, and probably a little challenging to do as a post-processing exercise.
Okay, thanks. The next question is, in terms of thermal modelling for REBA Stage 4 projects, could you ignore modelling the building using HVAC modelling and just use Apache Sim?
The question there has to be, which I kind of touched on in my element of the presentation, is how dominant is that load going to be in the overall stack up of total energy use. The more demand to condition the building, either heating or cooling, is, the more accurate I would think you would want your prediction to be. So if you're finding that your building load is not dominated by the environmental treatments, keeping it simplified is probably okay, unless you're trying to make progress with the assessment of your energy in use, in which case you might go down a HVAC route. So it very much is asking yourself the question is, what do I want to get from this operational energy model, and how accurate do I need it to be?
Yeah, I would echo that, Phil. I mean, I think it comes into the fact that you would probably already answer that, maybe even at stage 2, because you would have planned out and performed some error analysis to give you that feedback, so that you would be able to then plan and account for whether you would need an HVAC network, or whether an Apache systems approach would maybe be enough for your building.
Yeah, this comes back to the sort of planning stage that you talked about.
Okay, we're starting to run out of time. We might have to follow up some questions by email afterwards, but I'll try and wrap a couple of questions into one to finish. So someone's asking if you can provide guidance about introducing internal gains profiles. Should they be based on recording data from the actual building, or is the guidance that suggests the profiles? If you don't have the data before the building is occupied, what's the best approach? The sort of supplementary questions to that are, do you attempt to gauge how well educated building users are about energy efficiency and turning things off and so on? And do building occupiers normally or typically know their building well enough to help you answer these questions?
It's a good question. I mean, one of the suggestions that's made in TM54 is that you hold interviews with the building users to understand how they're going to use these buildings. Well, in my experience, that is seldom achieved, because they don't really understand the questions you're asking, or they're not available, or put it rather bluntly, the fee just does not allow it. So the answer to that is the general users don't really know how their buildings work, but in sort of 2020, as we sit here now, I think they understand a lot better than they did in, say, 2010.
Yeah. Okay. I think some of the questions are duplicated, but we have had a flurry of questions that I don't think we can tackle in the minute or so we've got left. So I think we can get the contact details for the people who've asked questions from the system, and perhaps I could ask the speakers to just check through and follow up on those post-presentation. I'd just like to finish by thanking the speakers. That was a very comprehensive and interesting presentation, as confirmed by the questions at the end. Several comments as well, not just questions, several people thanking you for the presentation and saying how informative it was. So I'll just finish by reminding everyone that the slides and the presentation will be available on our website from tomorrow on the news section. And to let everyone know that the next webinar in this series will be on the 18th of August, presented by Mariana Trusson on whole life costing for sustainable building. So hopefully we'll see some of you back on the 18th of August. In the meantime, stay safe and thank you all for attending.
Thank you.